In this video, we will talk about center of mass. We will give both the physical and mathematical definition of center of mass of a system of particles, followed by dynamics of center of mass. By dynamics, we mean we will explain how the concepts of velocity, acceleration, momentum, and force are associated with the concepts of center of mass. Finally, we will solve some problems to demonstrate the concepts presented. The following is the physical interpretation of the center of mass of a system. It is essentially a point in space that moves as if all the system's mass were concentrated at that point. So this point can be written in the form of coordinates like this. The mathematical definition of center of mass is as follows. So let's say you have a bunch of masses on an xy plane. So let's say you have mass 1, m1, there at a x-coordinate of x1 and y-coordinate of y1. Then you have another mass right there, m2. The x-coordinate is x2 and y-coordinate is y2, and so on up until n masses, the x-coordinate of which is xn and the y-coordinate of which is yn. Since the masses are on xy plane, there must be two coordinates for center of mass, the x-coordinate and the y-coordinate. So let's write down the x-coordinate for the center of mass. The definition is as follows. m1 times the x-coordinate of m1 plus m2 times the x-coordinate of mass 2, all the way until you cover the last mass, which is mn times the x-coordinate of that mass, divided by the sum of all the masses in the system, m1, m2, m3, all the way until mn. So that is the x-coordinate of that center of mass for this particular system. Now what about the y-coordinate? The y-coordinate of that center of mass similarly is m1 times the y-coordinate for mass 1, m2 times the y-coordinate for mass 2, m3 times the y-coordinate for mass 3, up until you cover the last mass, mn times the y-coordinate of that mass, mn, divided by the total mass in the system, m1, m2, all the way until mn. Of course, if the system is a three-dimensional system, namely the masses are distributed in three-dimensional space, there will be an additional coordinate, the z-coordinate, for the center of mass defined in a similar way. So the coordinate xcm, ycm, or xcm, ycm, zcm for the three-dimensional case represent the center of mass for such a system. Just to illustrate the idea, let's look at this very simple one-body system. So in this system, you just have one body, one mass, with mass 2 kilograms, whose coordinate is x equals to 2. There is no y-coordinate. So the center of mass for such a system is very simple. The mass is 2 times the coordinate is x equals to 2 over the total mass is 2. And that equals to 2 meters if x is quantified in the units of meters. Well, it makes sense in this case because the system consists of just one mass and the mass is 2 kilograms and the mass is at x equals to 2, so that must also be the point where all the mass is concentrated, namely the center of mass of the system. Let's look at the following system. So here you have three masses, 2 kg, 1 kg, and another 1 kg there. This is a two-dimensional system, so you should expect x and y coordinates for the center of mass. Let's compute the x coordinate first. So let's start with this 2 kg object from the left. So the mass is 2, the x coordinate is minus 2, plus the next term is this 1 kg object, the mass is 1, the x coordinate is of course 0, and the third mass, the 1 kg mass on the right, So the mass is 1 and the x-coordinate is 2. So you divide that sum by the total mass, which is 2 plus 1 plus 1, and you will get minus 0.5 for the x-coordinate. Now let's do the y-coordinate. So we'll do the same thing. We'll start with the mass from the left. So 2 kg, the y-coordinate for that mass is 0. And then the 1 kg, that one, the y-coordinate is minus 1. And the final term is the 1 kg on the right. So the mass is 1. The y-coordinate is again 0, divided by the total mass, 4 kg, mass of the system. And that's going to give you minus 0.25 for the y-coordinate. So that means the center of mass is at minus 0.5, minus 0.25. So where is that? So that is somewhere, say here approximately, right there. So this is the point where the entire mass of the system is concentrated. Now what happens if the masses in a system start to move? For example, m1 start to move with velocity v1, m2 starts to move with velocity v2, m3 with v3. What will happen to center of mass of the system? Well, generally the center of mass should move too. If so, what is the velocity of that center of mass point? That is what we want to address here, and therefore the acceleration, if any. So the masses are moving in 2 dimensions, so there must be x and y component to the velocity of center of mass. The x component of that center of mass velocity is given in a similar manner as the coordinates. So mass 1 times the x component of that velocity of mass 1 plus m2 x component of velocity of object 2, m3 the x component of the velocity vector of object 3, divided by the total mass m1 plus m2 plus m3. Now likewise, for the y component, you will get the following. So you represent the x components of the individual velocities with the y components, and that's it. Now likewise, if all the masses move with some acceleration, let's say all these masses are being acted upon by some external force, and by Newton's second law, all these masses will accelerate. So m1 with, let's say, a1, m2 with a2, and m3 with a3. So the center of mass will also accelerate generally. So the x component of that center of mass acceleration is given by the following. So mass 1 times the x component of the acceleration of object 1, mass 2 times the x component of the acceleration of that mass, and mass 3 times the x component of the acceleration of that mass. Now the y component can be written down similarly. So the y component of the acceleration of center of mass is m1 a1y, which is the y component of the acceleration of object 1, m2 a2y, and m3 a3y. Because velocity is a vector, we can write the final expression for the velocity vector of the center of mass in the following manner. So m1 v1, v1 is the velocity vector of mass 1, m2 v2, m3 v3 over the total mass m1, m2, m3. It's understood that we have combined the x and y component that we wrote down earlier in this vector notation form, like that. Another conclusion that we can make is that if we were to transfer the sum of the mass to the left-hand side, we would get the following expression. The total mass, m subscript t, is the sum of all the masses, times the velocity of this center of mass equals the sum of the individual momentum of the system, like that. So this is an important result that says the momentum of the center of mass is given by the sum of the individual momenta of the system. Likewise, the acceleration of the center of mass can be written in a vector form as well. m1 times the acceleration of m1 plus m2 times the acceleration vector of mass 2 plus m3 times the acceleration vector of mass 3 over the sum of m1 plus m2 plus m3. Now, if we transfer this term to the left, you get the total mass. By total mass, we mean the sum of the masses, m1 plus m2 plus m3, times the acceleration of the center of mass is quite simply m1a1 plus m2a2 plus m3a3. So the right-hand side of this equation is essentially the sum of external forces on the system. So what this equation is saying is that when a body or a collection of particles is acted on by external forces, the center of mass moves just as though all the mass were concentrated at that point, and it were acted on by a resultant force equal to the sum of the external forces on the system. Let's look at the following problem. Object A with mass 1 kg lies at the origin of an xy plane. Object B with 3 kg mass lies at point 1, 2 meters. At t equals to 0 seconds, a force Fa acts on object A and force Fb acts on object B respectively. Now we want to determine the displacement of the center of mass of this two-object system at t equals to 4 seconds with respect to its position at t equals to 0 seconds. Let's first determine the acceleration of the system. The acceleration of the system is given by the total mass times the acceleration of the center of mass equals the sum of external forces on the system. There are two of them. So the total mass is 1 plus 3, so that's 4. Acceleration of the center of mass equals the sum of the two forces. So F1 is that F sub A, F2 is F sub B. So that's going to give you minus I hat, 2I hat plus minus 3I hat plus 3J hat minus 3J hat, that is 0. And that's it. So that means your expression for the acceleration of the center of mass is minus 1 over 4 I hat meter per second squared. So that is the constant acceleration with which the center of mass is moving. Now from here we can determine the velocity of the center of mass, because after all it is just the integral of the acceleration of the center of mass with respect to time, according to what we have learned in our previous videos on motion. So when you integrate minus 1 over 4, it is quite simply minus 1 over 4 t I hat plus an integration constant, which we know is 0 because these two objects are not moving at t equals to 0. So the velocity of the center of mass is minus 1 over 4 t I hat in the unit of meter per second. Now position vector, because if you want to find displacement you need position vector. So position vector equals integral of velocity, and we know if you integrate t I hat with respect to d, the answer is minus 1 over 8 t squared I hat plus the position vector at t equals to 0 seconds. Now what we are interested in is the displacement. Displacement of the center of mass with respect to its position at t equals to 0, namely that. So all you need to do is to take the difference in the position vectors, and that's going to give you minus 1 over 8 t squared I hat. So the displacement at t equals to 4 seconds is minus 1 over 8, 4 squared at 16 I hat meters, or minus 2 I hat meters. So that is the answer. What that means is, under the influence of these two external forces on the system, the center of mass of the system has moved 2 meters to the left in an interval of 4 seconds. Thanks for watching.